Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, in this video, we shall define and explain the method to find the eigenvalues and eigenvectors for a square matrix. We shall solve two examples. In example number 1, we shall take a matrix of order 2 cross 2, and in example 2 we shall take a matrix of order 3 cross 3 to find the eigenvalues and eigenvectors. Let us see the definition of eigenvalues and eigenvectors. We say that a real or complex number lambda is called an eigenvalue of a square matrix A if there exists a column vector X such that this equation is satisfied. Here I is the identity matrix and the order of A and I must be same. X gives us the eigenvector, and it is a column vector, a matrix with only one column. Let us explain it a little more. If in a given question we are given a square matrix A of order 2 cross 2, then we shall take I of the same order. And in this case, the column vector X must be given by x1, x2, which is a matrix with only one column but with two rows. And now if A is a given matrix of order 3 cross 3, then I must be of the same order. And in this case, the matrix X must be equal to x1, x2, x3, which is a matrix with only one column but of 3 rows. To find the eigenvalues, we must solve this equation, which is determinant of A minus lambda I equal to 0. This equation is called the characteristic equation. When we solve this equation, we can get the values of lambda, such as lambda is equal to A, comma, B, and so on. And these are called the eigenvalues. For each value of lambda, we can find at least one eigenvector. To find an eigenvector for a given value of lambda, we must solve this equation to find the values of x. For example, if lambda is equal to A, we shall put the value of lambda, and then we have to simplify and solve this equation and find the values of x1, x2, and so on, and that will be our corresponding eigenvector. In example number 1, we shall learn how to find the eigenvalues and eigenvectors of a square matrix A. Let us start the solution. The first thing which we need is A minus lambda I. Let us put values. So we have 2, 2, 5, minus 1, minus lambda, and the value of the identity matrix is 1, 0, 0, 1. If we simplify this, we have A minus lambda I is equal to 2 minus lambda, 2, 5 minus 1 minus lambda. Let us say this is our equation number 1. Now, to find the eigenvalues, we must solve the equation determinant of A minus lambda I is equal to 0. Let us put values. So we have 2 minus lambda, 2, 5 minus 1 minus lambda equal to 0. To solve this determinant, we must multiply 2 minus lambda with minus 1 minus lambda and then minus 5 into 2. So let us simplify this. We have lambda square minus lambda minus 12 is equal to 0. And now let us factorize this. So we have lambda square minus 4 lambda plus 3 lambda minus 12 is equal to 0. If we further simplify this, we have lambda plus 3 into lambda minus 4 is equal to 0. And from this we have two values. Lambda is equal to minus 3 and the other value is lambda is equal to 4. And these two are the eigenvalues of the square matrix A. For each value of lambda, we can find at least one eigenvector. So let us take lambda is equal to minus 3. To find an eigenvector, we must solve the equation A minus lambda I into x is equal to 0. Let us put values in this equation. So from 1 we have 2 minus lambda 2, 5 minus 1 minus lambda into x1, x2, which is the value of x, and this is equal to 0. Now we can see that lambda is equal to minus 3. So if we put lambda is equal to minus 3, we have 5, 2, 5, 2 into x1, x2 equal to 0. Let us multiply these two matrices. So we have 5x1 plus 5, plus 2x2. And from the second row, we have 5x1 plus 2x2 is equal to 0. From this, we can get two equations. 5x1 plus 2x2 is equal to 0. The other equation is also same, which is 5x1 plus 2x2 is equal to 0. From any one of the above equation, we get the value that x2 is equal to minus 5 by 2 x1. And now we suppose that the value of x1 is equal to t. So therefore we get that the value of x2 is equal to minus 5 by 2t. Now putting these values in x, we have x is equal to x1, x2. So if I put the value of x1, which is t, then the value of x2 is 5 by 2 t. Now taking t as common. But to remove the fraction, let us take 2t as common. So we have 1 minus, sorry, this one is 2 minus 5. So this is the required eigenvector corresponding to the eigenvalue minus 3. But we can see that t here is any scalar. So any scalar multiple of this vector is an eigenvector of the given matrix A. So I can say that when lambda is equal to minus 3, we have an eigenvector 2 minus 5. This is only one eigenvector, but multiplying this vector with any scalar, you can get infinite number of eigenvectors for lambda is equal to minus 3. To find the eigenvectors for the other value of lambda, which is equal to 4, we will do the same procedure. So let us solve the equation A minus lambda I into x is equal to 0. And now let us put values in this equation. So we have 2 minus lambda, 2, 5 minus 1 minus lambda into the value of x, x1, x2 is equal to 0. And now let us put the value of lambda, which is 4. If we put the value of lambda, we have minus 2, 2, 5 minus 5 into x1, x2, which is equal to 0. Let us multiply these two equations. So we have minus 2x1 plus 2x2. Then 5x1 minus 5x2 is equal to 0. Now we have two equations. Minus 2x1 plus 2x2 is equal to 0. Let us say this is equation 2. And the other one is 5x1 minus 5x2, which is equal to 0. Let us solve equation number 2. So from equation number 2, we have x2 is equal to x1. If we solve equation 3, we can get the same value, x2 is equal to x1. So now let us suppose, let the value of x1 is equal to some scalar, let us say s. Then the value of x2 is the same scalar, s3. So we have the eigenvectors s, s. Let us take s as common. So we have 1, 1. So corresponding to lambda is equal to 4, we have an eigenvector 1, 1. But let us repeat once again that s is a scalar number. Let us say is a real number. So any scalar multiple of this is also an eigenvector. So there are infinite number of eigenvectors associated to the value lambda is equal to 4. In example number 2, we shall find the eigenvalues and eigenvectors for a 3 cross 3 matrix. The method is same. So let us find A minus lambda I, which is equal to 3 minus lambda minus 1, 2. 3 minus 1 minus lambda 6 minus 2, 2 minus 2 minus lambda, and let us say this is our equation number 1. To find the eigenvalues, we shall solve the equation determinant of A minus lambda I is equal to 0. Let us put values from 1. So we have 3 minus lambda minus 1, 2. 3 minus 1 minus lambda 6 minus 2, 2 minus 2 minus lambda, determinant is equal to 0. And now let us expand this determinant. So if we expand, we can get 3 minus lambda into 2 plus lambda plus 2 lambda plus lambda square minus 12. And now minus, but the sign of 1 is minus, so minus into minus plus 1 into minus 6 minus 3 lambda plus 12. And the next term is plus 2 into 6 minus 2 minus 2 lambda is equal to 0. Now, if we further simplify this, we get lambda cube minus 12 lambda plus 16 equal to 0. And now let us find the roots of this equation. So by guessing, one root must be in the divisor of 16. So we can see that if I put lambda is equal to 2, this equation is satisfied. So lambda is equal to 2 is one root of this equation. And now to find the other roots, we can divide the given equation by lambda minus 2, or we can use the synthetic division. So let us use the synthetic division. I am writing the coefficients. The coefficient of lambda cube is 1. The coefficient of lambda square is 0, minus 12, and then we have 16. And now let us use the synthetic division. I will write the root here. Now 1 into 2 is 2. I get 2 here. 2 2s are 4. I get minus 8 here. Minus 8 into 2 is minus 16. So we can see the remainder is 0. So I get lambda square plus 2 lambda minus 8 equal to 0. And now let us factorize this. So I have lambda square plus 4 lambda minus 2 lambda minus 8 equal to 0. And if we further simplify this, we can get lambda plus 4 into lambda minus 2 is equal to 0. So we have two more roots. Lambda is equal to minus 4 and lambda is equal to 2. So all the eigen values of this matrix are minus 4, 2, and 2. So we have 3 eigenvalues for the given matrix. 2 is repeated and minus 4 is a distinct real root. Now let us find eigenvalues corresponding to the eigenvalue lambda is equal to minus 4. So we must solve the equation A minus lambda I into x is equal to 0. let us put value of a minus lambda I from 1. So from 1 we have 3 minus lambda minus 1, 2. 3 minus 1 minus lambda 6 minus 2, 2 minus 2 minus lambda, and the value of x, let us say it is x, y, z, which is equal to 0. Now if we put the value of lambda, which is equal to minus 4, we have from here 7 minus 1, 2, 3, 3, 6, minus 2, minus 2, and minus 2 plus 4 is 2 into x, y, z equal to 0. Let us multiply these two matrices and we have three equations. 7x minus y plus 2z equal to 0. 3x plus 3y plus 6z equal to 0. Minus 2x plus 2y plus 2z equal to 0. So now we have three equations. Here we use the method of cross multiplication, which is also called the Kramer rule. So we can use any two of these equations. This is equation number 2, this one is 3, and this one is 4. So I will solve 2 and 3, but you can take any two equations. So according to that method, we write x equal to minus y equal to z. Now x is divided by the determinant. So we will ignore the x variable. So we can write the coefficient of y and z. This is minus 1, 3, 2, 6. Now in case of y, let us ignore y. So we can write 7, 3, and 2, 6. And now in case of z, we shall ignore the variable z. So we can write 7, 3, minus 1, 3. And now we put this thing equal to t. So let us simplify this. From here we can get x divided by, it is just a determinant. You can just simplify the determinant and you can get minus 12 here, which is equal to minus y divided by, we can get 36 here, which is equal to z, and divided by, we can get 24 equal to t. Now from here we can write x over minus 12 is equal to t, and this gives x is equal to minus 12t. From the other one we get minus y over 36 is equal to t. This will give us y is equal to minus 36t. From the third one we get z divided by 24 is equal to t, which gives z is equal to 24t. Hence we have the eigenvector x is equal to x, y, z. Let us put the values. So we can write minus 12t minus 36t, 24t. And let us take minus 12t is common. So we have 1, 3, minus 2. So this is the required eigenvector. So I can write here that with respect to lambda is equal to minus 4, we have the eigenvector 1, 3, minus 2. Any scalar multiple of this vector is an eigenvector corresponding to lambda is equal to minus 4. So there are infinite eigenvectors. To find eigenvectors when lambda is equal to 2, just remember that 2 is a repeated eigenvalue. 2 occurs 2 times. So we will proceed as usual. We must solve the equation a minus lambda I into x is equal to 0. And now let us put value of a minus lambda I and x. So from 1 we can write that the value of a minus lambda I is 3 minus lambda minus 1, 2. 3 minus 1 minus lambda 6. The third row is minus 2, 2 minus 2 minus lambda. And now let us multiply this matrix with x, which is x, y, and z. And this is equal to 0. The value of lambda is 2. Let us put the value of lambda. If I put lambda is equal to 2, we get 1 minus 1, 2. 3 minus 3, 6. Minus 2, 2 minus 4 multiplied with x, y, and z, which is equal to 0. Now let us multiply these two matrices. So I get x minus y plus 2z is equal to 0. Then I get 3x minus 3y plus 6z is equal to 0. And now from the final row, I get 2x plus 2y minus 4z is equal to 0. So the next task is to solve this system of equation. So I would like to suggest all the students, when you have repeated eigenvalues, you should use the row operation, which is called the Gauss elimination method or the Gauss-Jordan elimination method. So first of all, we need the augmented matrix for this system. So the augmented matrix is the augmented matrix is 1 minus 1, 2, which is equal to 0. Then 3 minus 3, 6, which is equal to 0. Minus 2, 2 minus 4, which is equal to 0. So I will draw a line here. Now the task is to reduce this matrix to the echelon or reduced echelon form. So we need that this number must be 0 and this number must be 0. So we need a row operation. Let us apply the row operation. So the first row operation, which I would like to make 3 as 0, is R2 minus 3R1. And to make minus 2 as 0, we need the operation R3 plus 2 R1. So let us write row number 1 as it is. 1 minus 1, 2, and this number is 0. And now if I apply operation, I get 0, 0, 0. Similarly, from the second operation, I get 0, 0. And these numbers are as it is. So now from here, I can write from the first row. x minus y plus 2z is equal to 0, which can be further simplified as x is equal to y minus 2z. Now we put, let y is equal to t and z is equal to k. So x is equal to t minus 2k. Hence, the eigenvector x is equal to x, y, and z becomes, let us put values of x, which is t minus 2k. The value of y is t, the value of z is k. And now let us simplify it a little more. So I can write t 0 plus I can write minus 2k 0 k. Let us take t as common. So I can write x is equal to, let us take t as common from the first one. So I have 1, 1, 0. And let us take, now let us take k as common from the second matrix. So what we get? We get minus 2, 0, 1. So we have two eigenvectors associated to lambda is equal to 2. And let us write this. Hence we can say that when lambda is equal to 2, we have two eigenvectors. 1, 1, 0. The other vector is minus 2, 0, 1. Again, I will repeat that 1, 1, 0 or minus 2, 0, 1. We can say this is one eigenvector, but any scalar multiple of this vector is another eigenvector associated to lambda is equal to 2. So there are infinite number of eigenvectors. That's all.